the same confined space, there is an infinite number of parallel realities that actually can create a powerful or less powerful form of God equals mc squared as we know it.
What if a single conversation could make us rethink everything we know about space? Deep beneath Switzerland, a ring of powerful magnets fires beams of particles at nearly light speed. Some believe those collisions may have ripped open a doorway to another world. Today, we examine that rumor through the perspective of Joe Rogan and a 13-year-old kid. We ask the questions that spark curiosity, search for the facts that ground us, and trace a path from rumor to reality. But this wasn't just a feel-good interview with a gifted kid. As the conversation unfolded, something strange occurred, something that made even Rogan pause. Was Max noticing patterns others missed? Why Joe Rogan brought in a genius kid? When Joe Rogan learned about Max Laughlin's physics videos, he reached out right away. Max is 13 and posts under @MaxLaughlin on TikTok. His short clips explore memory quirks and particle collisions. One video on the Mandela effect using colored cards has passed 5 million views. It caught widespread attention, leading to rapid sharing. In February 2025, producers invited him to appear on episode 1912 of The Joe Rogan Experience. Max spent 2 weeks studying official CERN reports and watching brief LHC documentaries. On April 10th, he flew into Los Angeles for the show, meeting Joe Rogan and the crew. They moved to the set, a simple studio with 2 chairs and a round table. As cameras rolled, Rogan introduced Max as someone who explains complex ideas clearly. He then asked how Max first developed his interest in science. Max said he built a telescope at age 8 to view moon craters. Later, he assembled a radio using soldering tools to learn electronics basics. Max also earned first place at his county science fair for a homemade cloud chamber that revealed particle paths. Rogan brought up the portal claim linked to CERN's collider. Max described the facility as a 27-kilometer ring beneath Geneva designed for proton collisions. He explained that the goal is to recreate early universe conditions and search for new particles. He added that CERN publishes every result online and no portal report exists. Rogan commented on how quickly rumors spread on social media and asked how Max checks strange claims. Max replied that he starts with lab websites. He also reads articles on respected physics blogs and watches lecture recordings by university researchers. During the discussion, Max sketched a basic collider layout on paper. The conversation stayed grounded in facts. Rogan noted that Max had reviewed dozens of summaries from high-energy physics groups before arriving. Max Laughlin is a genius. No ordinary 13-year-old could hold such deep knowledge of complex topics. It is extremely rare, nearly 1 in a million. Through him, a broader discussion emerged among science giants seeking to understand and explain what truly lies behind Max's insight. But here's the twist. Max wasn't simply repeating facts. He spoke with the steady confidence of someone who had seen something he couldn't unsee. So what exactly did he uncover? Inside CERN, what really happened underground. Inside CERN, a tunnel runs beneath farmland near Geneva, along the border of France and Switzerland. It stretches for 27 kilometers in a circular loop. Inside that ring, machines operate around the clock. Liquid helium keeps the space cold, dropping temperatures to -271 degrees Celsius, colder than deep space. Superconducting magnets line the walls to guide particles, shaping the paths of proton beams on a precise track. 2 beams circulate in opposite directions. Powerful radio waves accelerate them with each lap. Sensors check their position thousands of times each second. When the beams reach full speed, they enter special crossover points. There, protons collide. The energy released mirrors conditions just after the Big Bang. Each crash creates a burst of new particles. Detectors surround these points, resembling giant cameras made of metal and silicon. Atlas and CMS stand out as the largest, each weighing thousands of tons. They capture sprays of subatomic particles flying outward. Tiny chips record data on mass, charge, and speed. High-speed electronics convert signals into usable data. Systems are tested before every run. Technicians monitor every channel to detect faults. Above ground, engineers work in control rooms filled with screens and consoles. They manage beam injections, magnet currents, and safety systems. Thousands of computers gather and process data from each experiment. That information spreads through a global network of data centers. Researchers from over 100 countries log in to analyze results. Teams meet daily to review findings and plan future runs. Scientists at CERN focus on several core goals. One is studying the Higgs boson, the particle that gives mass to others. Another is searching for dark matter, the invisible substance shaping galaxies. They also explore how gravity behaves at small scales, testing whether space obeys known laws under extreme energy. Some theories suggest extra dimensions beyond those we observe. If particles enter those tiny spaces, they might vanish from detectors. Physicists search for missing traces in the data. Energy gaps can hint at new directions for study. Each clue informs future experiments. No test has ever torn space or opened a doorway to another dimension. The collider simply studies particle behavior under intense forces. Every result enters open databases for public review. CERN posts regular updates online. Plans are underway to upgrade the collider for higher collision rates. The high-luminosity LHC will increase collisions tenfold, helping reveal rare events current detectors miss. Other proposals include a new ring collider twice as wide. Each project pushes science into unexplored territory. But while physicists saw patterns in particle trails, the Internet saw something else, a doorway. Could the world's most advanced science experiment have accidentally sparked a story no one expected?
Where did the portal story come from? The story began when someone claimed to see a strange light near a Large Hadron Collider tunnel. They described a flicker of color at an access hatch late at night. That account caught the attention of readers drawn to unusual science news. Soon, a writer for a satirical site turned it into a headline about CERN opening a gateway to another world. Many readers assumed it was real. Within hours, social media pages linked to the article as proof of a secret experiment. Video channels chasing shock value posted titles like "CERN Portal Shocks Scientists." They used stock footage, lab tour clips, and dramatic narration. Each upload promised exclusive evidence but recycled the same satirical text in new words. Search engines added fuel. Early searches for CERN Portal ranked the satirical link at the top. Readers mistook it for an official source. Those headlines reached millions before corrections appeared. Conspiracy websites added layers, tying the idea to ancient myths or secret military projects. None offered real documents. No engineer or scientist spoke on record. Quotes could not be traced. Fact-checking groups investigated. They reviewed CERN press releases, lab reports, and archives. They found no portal experiment. Their summaries noted CERN publishes all technical notes publicly. No memo mentioned a doorway. The conclusion was clear. The claim was false, born from satire. Max Laughlin saw the headline in a group chat and decided to verify it. He checked CERN's official site and found a statement denying portal tests. He downloaded the technical FAQ explaining why proton collisions cannot tear space. Max even wrote explanations outlining the collider's real purpose before appearing on the Joe Rogan show. On the podcast, Rogan and Max tracked the claim step by step, from a casual post to a viral headline. They compared the original text to CERN's official statements, showing how a joke became a sensation. But here's the twist. While Max dismantled internet myths, real physicists were exploring ideas even stranger. What if hidden dimensions weren't entirely fiction after all? What science says about other dimensions. Physicists have long considered that space might contain more directions than the three we see. In the early 20th century, mathematician Theodore Kaluza proposed a fifth dimension to unify gravity and electromagnetism. Later, in the 1930s, physicist Oscar Klein suggested these dimensions could be tiny loops too small to detect. These ideas laid the foundation for modern theories that attempt to explain forces and particles within a single framework. In recent decades, string theory expanded on those ideas. It describes fundamental objects as tiny vibrating strings and requires up to 10 spatial dimensions. The shapes of these extra dimensions, often called Calabi-Yau spaces, determine particle properties. If the shapes were different, the universe would behave in an entirely different way. However, string theory predicts an enormous number of possible shapes, making experimental proof extremely difficult. To test for extra dimensions, scientists search for deviations in gravity at very short distances. At the University of Washington, the EAT-WASH group positions metal plates just a millimeter apart. They measure gravitational forces using precise torsion balances. Results down to fractions of a millimeter match Einstein's predictions, ruling out large extra dimensions at those scales. High-energy experiments at the Large Hadron Collider offer another test. When protons collide, they release immense energy that could reveal hidden dimensions. Detectors surrounding collision points track every outgoing particle. Researchers look for missing energy, signs that particles may have escaped into unseen space. After studying billions of collisions, no unexplained gaps appear. These results place strict limits on dimension size, pushing them below 10 to the minus 19 meters. Astrophysical observations add further limits. Cosmic rays colliding in Earth's atmosphere reach energies higher than those at CERN. Telescopes and balloon experiments monitor these events for mini black holes, predicted by some theories involving extra dimensions. None have been observed. Studies of supernova cooling and the cosmic microwave background also align with standard physics, showing no extra energy loss. Dark matter remains one of astronomy's greatest mysteries. It affects gravity but emits no light. Some theories link dark matter to extra dimensions. Underground labs such as Xenon 1T and Lux Zeppelin search for rare interactions between dark matter and atomic nuclei. So far, detectors have only recorded background noise. No confirmed signal has emerged. String theory attempts to unite all forces into one framework. It treats particles as loops of energy and relies on extra dimensions for the math to function. Each dimensional pattern creates a different possible universe. Physicists analyze these patterns to find one that matches our reality, but the vast number of possibilities makes progress slow. Gravitational wave observatories like LIGO and Virgo detect ripples from black hole mergers. Extra dimensions could alter how these waves travel. So far, observed signals align perfectly with standard physics. Researchers continue refining measurements with increasingly sensitive tools. But what if the missing piece isn't in our universe at all? What if the silence in our detectors is the sound of something slipping away? Could we be looking in the wrong dimension?
Highlights from the JRE conversation. Max Laughlin began by explaining how CERN's collisions probe the smallest components of matter. When protons collide, they recreate conditions present just after the universe formed. Detectors record showers of new particles. By studying this debris, scientists test theories about forces and the building blocks of reality. He moved on to parallel worlds. Max explained that some physics models allow multiple versions of reality to coexist, each governed by slightly different rules. At extreme energies, particles might move between these versions.
He pointed to the Large Hadron Collider as one place where such energies exist. If particles escaped, detectors would show missing energy. So far, all observed gaps match predictions, placing tight limits on such behavior. Max then discussed the double-slit experiment. He described how particles passing through two slits form wave-like interference patterns. When observers measure which slit is used, the pattern changes. He used this to illustrate how measurement influences outcomes in quantum physics. Scientists still debate what this means for reality itself. He explored the idea that everything vibrates at specific frequencies. Matter, he said, is energy in motion. Vibrations determine particle properties and forces. When energy changes, particles can appear or vanish. He referenced the 2012 discovery of the Higgs boson as a turning point. That particle explained how others gain mass. CERN confirmed it by tracking Higgs decays into photons and other particles. Max also addressed dark matter. He explained that most matter in the universe is invisible and interacts weakly with known forces. Underground detectors worldwide search for rare collisions, but have found no clear signals. Collider data could reveal dark matter if it appears alongside known particles, but none have been detected, narrowing the search. Throughout the discussion, Max connected experimental results to larger questions. He focused on data, clearly outlining each step. His overview captured modern physics, from particle sprays and massive detectors to delicate measurements deep underground. But here's the twist. Max's clarity made one thing undeniable. For everything we've discovered, the biggest mysteries remain untouched. So, what are we still missing? Still unanswered, the big questions remain. Despite decades of research, major puzzles persist. One of the largest is dark matter. Observations show more gravity than visible matter can explain. Scientists search for weakly interacting particles. Detectors like Xenon 1T in Italy and Lux ZEPL in the US use liquid-filled tanks to capture rare flashes of light. So far, no confirmed detections exist. Each experiment eliminates more candidates. Another mystery involves neutrinos, ghost particles that pass through Earth almost untouched. Experiments such as Super Kamikonde and IceCube track neutrinos from space and reactors. They discovered neutrino oscillation, earning the 2015 Nobel Prize. Yet the origin of neutrino mass remains unknown. New projects like the Deep Underground Neutrino Experiment aim to measure these effects with greater precision. The hunt for new forces continues. Gravity works well at large scales, but resists quantization. Proposed observatories, such as the Cosmic Explorer, hope to detect tiny ripples in spacetime. If gravity behaves differently at short distances, anomalies could appear. Plans for future particle colliders are also moving forward. Projects in Europe and China aim to exceed the LHC's energy. Such machines could reveal heavier particles, extra dimensions, or early universe conditions with greater clarity. Funding and locations are still in discussion, but ambition remains high. Scientists also ask why matter dominates over antimatter. The Big Bang should have created equal amounts. Experiments at CERN and in Japan study particle decays for tiny imbalances. Results show differences, but not enough to explain the universe we see. Efforts to unify gravity and quantum mechanics continue through theories like loop quantum gravity and string theory. None have produced testable predictions yet. Quantum sensors and ultra-cold atoms may soon probe gravity at microscopic scales. Even the Higgs field raises new questions. Precise measurements may reveal hidden interactions. Future experiments will search for subtle deviations from current models. Though answers remain elusive, these questions drive progress. Scientists collaborate worldwide, share data, and refine ideas as new evidence emerges. The path ahead is long, but the mysteries point toward discoveries still waiting beneath the surface.
So now, from dark matter to hidden dimensions, we've only scratched the surface. What if the biggest breakthrough of our time is already here, just waiting for someone to see it first?